Hi, everybody. We're back. So, up next, we have Datagram, an expert in the field of cybersecurity, hacking, reverse engineering, binary exploitation, and physical security. He runs the upcoming Layer 1 Security Conference and is a founding member of the LA Hackerspace, Null Space Labs. Today, he'll be presenting a workshop on binary exploitations for beginners.
Okay, so welcome. My name is Data. Today we're going to talk about Intro to Binary Exploitation. We have quite a while ahead of us. I tried to make it as beginner friendly as possible, but we're going to kind of play it by ear. If you have any questions, just throw them in the Discord or in the chat panel, and I will pull that up so I could see it. Okay, cool. All right. So if you wanted to know about me for some reason, my name's Data or DG. I hack stuff. I think a lot of you have met me before at all the various conferences and hackerspaces and other kind of hacker and security related things in Southern California and nearby areas. But the things that I do are, quote, cybersecurity. So my specialties are binary analysis, binary exploitation, which are kind of the focus of today's talk, as well as reverse engineering, a good amount of penetration testing, and quite a few of you know me from physical security. So Cal Poly Pomona has their annual tech fair, and I'm often there showcasing lockpicking and kind of related stuff in the lockpicking workshop area. Lockpicking Village, I should say. If you've been to DEF CON, you've probably seen me at the Tampa Revenant Village. That's another physical security thing I'm interested in. And as many of you know, I run Layer 1, the Los Angeles security conference that is coming up in May. And I'm also one of the founders of Null Space Labs, which is a LA hackerspace. So I always forget, and frankly, the amount of technical material is going to make a lot of people tune out about 5 minutes in, so we had to put this up front. But come to Layer 1 2021, we're virtual this year, much like Tech Symposium. So I put the Discord link and the Twitch link there. We'll be at the end of May, and it's all the same Layer 1 stuff you've come to love and enjoy, just not in person. So we're going to try and make it as close to the original experience as possible, but obviously Layer 1 physical space, there will be some things missing. So without further ado, let's talk about what is binary exploitation. So in a nutshell, it is finding and exploiting vulnerabilities in binary applications. So when we say binary, typically we mean executable. So this is pretty platform independent. This could be on Windows, this could be on Linux, Mac, it could be for servers, it could be for clients. Anything that runs software, we're interested in identifying and exploiting vulnerabilities. When people specifically say binary exploitation, what they usually mean is some kind of memory corruption with the express goal of taking over a program to get it to do things it wasn't programmed to do. So that might sound strange, like how do you get something to do something it wasn't programmed to do, but we're going to talk about kind of how that works and some background there. And it covers this kind of wide range of vulnerabilities that you've probably heard of before, things like buffer overflows, stack overflows, heap overflows, integer overflows, logic errors, order of operations errors, format stream vulnerabilities. Obviously a lot more than just what's listed here, but these are kind of the common ones that come up. So that's kind of what we're thinking about today. Why should you care? So I find that there's a pretty big disconnect in terms of like understanding why vulnerabilities matter, right? So some folks are like, well, I'm not a target, it doesn't matter, or my stuff is not important, or nobody would come after me, I don't have any enemies, etc. But I think some folks downplay that everything that runs on your computer is executable, right? So logically, if everything's executable and we're trying to find vulnerabilities in those executables, then everything running on your computer, no matter how innocuous, is potentially exploitable. And often even the smallest things can be chained together to go from some low impact vulnerabilities to a full chain of exploits that leads to like a full compromise of the system. So just think about this, right? If executables have vulnerabilities and everything running on your system is executable, can everything be exploited? So I think many of you, again, being in this world, would say, well, obviously, but do you really consider everything that you're running, right? So the Zoom software we're on now, am I broadcasting something to you that exploits a flaw in Zoom that lets me take over your systems? Did you think about it before you clicked run this exe from a Chinese company that you've never heard of? Did you think about it before it said, hey, by the way, I need admin privileges? You know, there's cameras and there's microphones involved. You know how it is. Let me have admin privileges, right? What about Discord, right? This conference is also on Discord. What if there is a vulnerability in Discord? Everybody in the Discord server is potentially vulnerable to this, right? What about your browser? This is maybe a little more familiar, right? Everybody knows don't click suspicious links, but why? And the answer is browsers have vulnerabilities, and those vulnerabilities can be exploited to get access to your system. Same goes for literally everything else, but some examples I put here are things that run on the network, right? Network services. Obviously, your web server is exposed to the internet. Obviously, your operating systems that you're running, whether it's Windows, Linux, lots of vulnerabilities come out year after year. Even for these relatively mature pieces of software, right? And then there's some that people really don't consider. Like, what about the piece of software that renders the fonts on your screen? What about the piece of software that's rendering this image for my Zoom call again? So literally everything. And you might go, well, Data, my fonts are fine. I've never had a problem with fonts. Well, there's a lot of vulnerabilities, even in the smallest of component, right? So there's definitely things like font rendering vulnerabilities. And if folks are going through the trouble to find vulnerabilities in font renderers, you can bet that they're looking at your browser, your Zoom software, your Discord software, et cetera. And now some of you might go, well, Data, you're old, and these vulnerabilities are old. These are from 2015. I don't even remember what computer I was using in 2015. And you're not wrong, which is why I've also included one from July 2020. So it's not like this is an old thing or people don't do it anymore. This happens year after year. Every piece of software has vulnerabilities published. And those that don't are often just because they are not popular enough to be focused on by hackers, not because they're not vulnerable, but because people haven't cared to look. And that's kind of a scary thought, is just because it's not published doesn't mean it's not vulnerable, and kind of that train of thought there. So anything you run, you should be concerned about it if you're concerned about security. And this goes for you as a person, this goes for you as an employee or as a business owner, kind of from low level to high level, all this matters, right? Everything has a potential impact. So let's say you're interested in binary exploitation, not just for the fun of it, but like who actually does this, right? So obviously there's this kind of quote unquote security research thing, which are people like Google Project Zero, who do very specific high level exploitation and vulnerability analysis against specific targets. In the case of Google Project Zero, it's typically browsers or operating systems, as those are used by pretty much everybody who uses a computer. But there's also this field of generic exploit development. So there's folks out there who specifically look for vulnerabilities with the express purpose of either selling them on the black market or, quote, the dark web, or on to the manufacturers or the developers of the software in the form of bug bounties. There's also a lot of crossover with reverse engineering. Typically, to do bug bounties, you're doing some mixture of reverse engineering followed by exploit development. So with reverse engineering, you identify the problem. With exploit development, you provide a sample script or file or something that showcases the problem so that it can be reproduced by the developers. Again, typically to get fixed, but also potentially so that somebody else can make an exploit out of it and then go attack people on the internet or wherever that might be. And then finally, kind of, sort of, penetration testing uses this. So I would say the distinction here is that 99.9% of penetration testers are not writing an exploit while doing a penetration test. But they are using something pre-made and pre-packaged. So think of things like Metasploit or any of the other kind of exploitation frameworks that have a big library of pre-packaged customizable exploits so that you can point them at an IP and push enter, and then magically you've hacked the system, right? So in a way, they use binary exploitation, but I wouldn't say that people doing penetration testing are too deeply involved in the field other than using something that's already been made for them. At least in my experience. I'm sure it varies. And often this is not a skills thing. This is a time limit thing, right? So most penetration tests take a week, 2 weeks, 3 weeks at the most usually. And it's rare to have the time to fully realize an exploit from start to finish, more so than a skills or knowledge thing. So that's been my experience. I'm sure there's others, but those are probably the big five. The other place that this is done is obviously capture the flag competitions. And I know some of you are familiar with this, but for those that aren't, I wanted to give a description. So CTF stands for capture the flag. And the basic premise of a CTF is that you are presented a problem, a technical problem of some sort, and you need to figure out a password, also known as the flag. And the CTF website will show you the problem, and then it'll say, hey, tell me the answer. And if you get the answer right, you get points. And then you trash talk your friends because you got it before them. And that's at least my experience. But problems can come in a variety of categories. So there's exploitation problems, which can be binary exploitation. They can be web exploitation and other kind of variants of this. There's obviously reverse engineering, web problems, forensics problems, crypto problems. There's a whole slew of categories. And for me, I enjoy the binary exploitation and reverse engineering, obviously, but others find interest in the other categories. So there's something for everybody, is I guess what I'm getting at. And part of the fun is that you don't really know what you're getting into when you sign up for one, because if you already knew what the problems were, you'd already potentially know the answer. And there's so many CTFs going on all the time that they try really hard to distinguish and differentiate themselves to provide new challenges to the people that play a lot. So sometimes the problem's a website, sometimes it's an executable, sometimes it's just a really short thing of source code. Sometimes it's images, audios, etc. You get the idea. And figuring out what the problem is and how to go about solving it is sometimes a major focus of the challenges. So for me, I found these very helpful to be presented a wide variety of problems, specifically for binary exploitation and reverse engineering, that helped me figure out what I was good at, what I wasn't good at that I needed to go learn more about, and what stuff I really didn't like, which is crypto and forensics for me. But for you, those might be the things you like. So I strongly recommend these as like a learning tool, kind of regardless of what you currently like. And again, for me, this also helped me identify the things I wanted to go further with. Like, that was very interesting to me. Let's learn more about that. Let's do that again in the next one. So as a beginning student, for some of you, you may not be sure what you're interested in. And I found that the CTFs were a pretty quick way to tell me what I did and didn't like. So I hope that holds true for you guys as well. So what we're going to do today is I'd like to walk through some Pico CTF 2019 problems. So these are some CTFs run for like a limited period of time, like a weekend or a week, and then they're gone forever. A very small number of them leave the problems up so that you can do them forever. And Pico CTF is one of those. So their 2019 one is the most recent full challenge they've done. Funnily enough, on Tuesday, I don't know the date, but the Tuesday coming up in a few days is Pico CTF 2021. So obviously they took a year off for COVID. But for Pico 2021, that starts on Tuesday and it runs for, I want to say, until the end of the month, something like 2 or 3 weeks. So if you like this and you had fun and you want to try it in a fresh live one, that'll start Tuesday. But for now, if you'd like to follow along with today's workshop, then go to Pico CTF 2019, either Google it or type this link and make yourself an account real quick. It should take just 2 minutes to fill out the username and password and all that, and then activate your account with your email. Specifically, we're going to be focusing on the binary exploitation category, but I do, again, recommend that you try other categories later, find out what you like and don't like, and what you want to learn more about. So I'll leave that up for a second. The Q&A is currently harassing me, saying I'm trying to recruit more CTF players, and they're not wrong. They're just misguided. So hopefully those of you who are going to do this have made an account. When you get logged in, I have a teacher account, but all you really want to get to is challenge problems here on the top bar. You should see there's quite a lot of stuff listed. So the first thing I'm going to do, actually, I'll give folks a second just to make their account and get logged in. One thing I'll explain while that's going on is that at the top, there's a shell button. So most of the time, this is not offered by CTFs, but Pico offers a web shell. So no matter what computer you're on, as long as you have a browser, you can pull up an SSH shell to the servers that all the problems are hosted on. I frankly can't use this because I use Control W pretty religiously in the terminal, which to show you, like if we type some words, it'll delete back a word. And every time I try and do this in the web, I close the tab instead. So I look like a moron, and then I start swearing, and the talk's all downhill from there. So if you don't want to use SSH or PuTTY, you can click the shell button up top. But otherwise, I am going to SSH in. And if you want to know how to SSH in, you need to SSH to 2019 shell1.picoctf.com with your account name. The first time you connect, it'll make a SSH account for you. And then the second time you connect, you'll be prompted for your password and you'll get logged in. And then from there on, you can do everything in the shell. Obviously, they don't want you to do anything bad. So if you do anything to crash the server, overload the server, or anything not related to the problems, you will probably get your IP banned. So be careful about that. If you want to like mess around in Python or mess around with like general Linux stuff, I would say use your own system or a virtual machine. Don't do it on the Pico servers because they can and will ban you, much for the reasons that Chris identified earlier, and that they don't want to have to pay a big AWS bill for people trying to do all sorts of file transfers and other shenanigans. So hopefully we burned enough time by now that you have made your Pico CTF account and you are at this challenge problems screen. Again, you'll see a lot of stuff. So what I'm going to do over here on the left is click only binary exploitation, and that'll filter everything else out. You can click solved or unsolved if you want. That'll hide something once you solve it, but it doesn't really matter for us for right now. So at the start, there's only 3 things unlocked, and this is a common thing in CTFs. You will have to unlock kind of the grade 1 problem before it gives you the grade 2 and so on. But we see that there are 2 things available. So you should see this. So while you guys are doing that, I will speak at you for a bit. So the first one is really simple, but it's just a reminder for folks if they are not super familiar learning Linux and being used to Linux. But the first one is called practice run 1, and it's literally just run a executable in the shell. And this is to get you familiar with using the shell and submitting a flag and seeing what a flag looks like. So if we read the challenge description, it says you're going to need to know how to run You're going to need to know how to run programs if you're going to get out of here. Navigate to this path, and the paths given are not always the same. So make sure you copy paste it from your side and don't try and copy mine because they are a little bit different. So if we copy this path, now we're going to go over to our shell. Oops, we'll see that I'm on my Pico shell. I'm going to CD over there, and I'm going to look at what's in here. We see that the only thing here is called run this. And the way that they do this, if you guys are curious, to prevent you from kind of getting further than you're allowed to or seeing flags that you're not allowed to, is that all the binaries are set UID or set group ID, I should say. So this means when you run it, you're not running with your user's permissions, or you're running with that specific problem's permissions. And that has kind of impact later on for some of the other challenges. But from here, we execute this, and we get a flag. So that's literally all it is for problem one, just to get you kind of used to using the shell, used to seeing what a flag looks like. So from here, we see that the format for the flags is Pico CTF, curly brackets, and then the flag itself. So different CTFs will do this differently, but we typically want to copy the whole thing, including Pico CTF, including the brackets. We'll copy that. And if we take that back over here and put it in our flag box and click submit, we'll see that, hey, we solved it. It says up in the top right, that is correct. See, it says we solved it, and now we have 50 whole points. So after following along with that, congratulations, you've solved your first CTF problem. I know that one was really easy. Most CTFs have something like join the Discord for 1 point or something. So there's always at least one thing you can solve in every CTF. So that's what I hang my hat on. I get my 1 point, and then I tell the rest of my team to do all the actual work. But hopefully we can go a little bit further today. After solving practice run 1, you'll see that overflow 0 unlocked. So now we can see the description for this. And if I didn't mention it before, there is a hints button. So you see you're on the solve tab for each of the problems. If you click hints, like let's see if we can show it for practice run. Click hints. It says, how do you execute a program in a command line? So I would say Picos are not the most helpful because it was meant to be a competitive thing. But there are a lot of like learning or teaching CTFs that will make the hints like a lot more verbose, in that they tell you like exactly what to Google, exactly what to kind of look up to get on the road to get the answer. And in very rare cases, they will like literally tell you the answer short of typing it for you. But I think if you need the hint, take the hint, but do everything in your power to solve it before you look at the hint. At least that's my perspective, and I'm sure that's Los Angeles hacker elitism hard at work, but that's my personal preference. So what else do we have? Let's see. We have handy shellcode and overflow 0. So kind of the flow from here on out is I want to explain the process as much as possible while still kind of fitting in our time limit. And binary exploitation is unfortunately one of those disciplines that has a lot of overlapping, very old, not old in the sense that it's outdated, but old in the sense that there's a lot of stuff piled on top of each other, technologies, and it's very hard to, in one sentence, describe everything that goes into exploiting something from start to finish. And what I often find is that folks will ask me, like, how do I want to exploit something, how do I do it? And I ask them to explain the exploitation process to me to kind of figure out where the gaps are. And it's very rare that people can explain it accurately, right? There's a lot of kind of hand waving and kind of making up for gaps in knowledge that people think will be okay, but you really have to do everything right to exploit stuff. There's not a lot of room for error, unfortunately. And we'll kind of see why. But end result is I'm going to explain a lot, and then we're going to do a little bit, and then I'm going to explain a lot, and then we're going to do a little bit. Hopefully having explained enough that at the end you can kind of crawl on your own through some of the problems after this. And there's lots of tutorials and write-ups and other stuff if you need help. Obviously, you're not going to learn everything there is to know in 90 minutes, but we're going to do our best. So the first bit of information we want to talk about, and this is probably something you've seen in a textbook that you snooze through while your professor was talking about it, is kind of how do we get from source code to executable? And then after this, we'll talk about what happens after we have our executable. So in a nutshell, I think many of you know some of this, but maybe not the whole process, is that you have your source code. In most programming languages, you're using some amount of library code, whether it's C or Python or Java. It's rare that you're writing every single piece of functionality yourself in the kind of core language, right? There's some amount of function calls or libraries or any number of packages you're adding that add the functionality you're trying to do. So some examples of this are all of the C standard library, right? So if you're using str copy, str format, all those various C and C++ functions are provided by a library. The same is true in Python. All those built-in functions are part of the quote built-ins package, which is just a library of code that's added in. So effectively, all that stuff gets put together in a big blob with your source code sent to the compiler. So the compiler's job is to translate source code to assembly code. And we'll talk a little bit more about what assembly is, but at a base level, it is a representation of your program for a specific processor and sometimes a specific operating system. And again, we'll talk about this a little bit more, but you generate assembly code. I'm sure some of you have seen it before. And that gets sent to an assembler. So the assembler's job is taking that otherwise human readable assembly code and compiling it, again, a second step of compilation into what's called an object file. So at this point, you've gone from source code, which is readable, to assembly code, which is also in many ways readable, though I guess that's debatable, to an object file, which is a pure binary format. So if you just open this up in a text editor, you'll just see gibberish, right? Because it's all binary packed data. And then after this, this is sent to what's called a linker. And there's also a step in here missing called the loader. And the linker's job is if you have any library code that's dynamic, it will put in kind of placeholders for when it's run on a different system. So in modern computing, it's pretty rare that we have what's called static library code, which is library code that's compiled directly into the program. Instead, what we have is typically dynamic libraries. So things like DLLs in Linux, these are called SOs or shared objects. The idea being that you don't need to include all this code in your program. You provide it to the user with these placeholders, and then the user system is expected to have whatever libraries are necessary to make this work. So some common ones in Linux are things like libc. Other pretty common ones are things like libxml, a variety of GUI things like libqt or libwx, etc. So there's quite a lot of libraries, right? Because again, very few people write their code purely from scratch without the use of any library. But in the executables, we're putting in placeholders for all that. And so this is why if you've ever run something on Linux and it says, hey, I can't find this shared object, it's missing some library that your system needs to run that executable. At the end of all this, we get our executable popped out by the compiler, and in the background, the assembler and the linker. And at this point, our executable is ready to be run on our target platform. But how does this work? So when you push enter, when we did run this on the command line, what happens? And frankly, it's very complicated. So this is like the high level bird's eye view. But the short description is that it reads the file, the executable file itself. And the executable file has a format, and that has a header, and it has your executable code buried somewhere inside of it. And the header tells the system running the executable things like, what do you need to execute this? Like, am I even compatible? So this is things like 62-bit versus 32-bit. Is it compiled for an Intel processor? Is it compiled for an ARM processor, et cetera? And if all those match up, if you have support for whatever the executable is, then the system starts copying resources into memory. So it copies what we're calling environment resources. And this is frankly a really complicated topic we're not going to get into, but it's things like your user's environment and other things specific to the person or the account running the process. Those get copied into memory. Then the program itself gets copied into memory. The system will check we talked about how there's dynamic libraries and all that. The system will check which ones of those are required and load the necessary ones into memory if they're not already there. If there's any what we're calling immediate dynamic needs, it'll resolve those right away. So sometimes in most executables, they won't finish loading something until the first time it's asked for. And this is like a performance trade-off thing in that it's faster to load initially, but slower the first time you ask for something. And then after that, it's fast for everything. And then assuming all this goes to plan and everything's loaded up into memory and everything's fine, then the OS will transfer execution to what's called the program entry point. So this is the first instruction in assembly of your program as compiled and all that. And at that point, your process and all the other stuff has been handled by the OS and your program officially starts and can run. So that's kind of the bird's eye view, right? But I meet a pretty small number of folks who can tell me this, even though this is the bird's eye view. Okay. And again, feel free to ask questions whenever. I am looking. Hopefully somebody's listening. So if you needed a kind of more visual view of this, your executable is on the left, and your executable is made up of a number of sections. So there's the header. ELF stands for executable and linking format. This is the most common type of executable in Linux and Mac. In Windows, this is called PE, or portable executable, but it follows more or less the same structure. There's some program headers, which are things defining the layout of your program as it relates to memory and execution and permissions within memory and all sorts of stuff like that. And then you have your big block of compiled code. And at some point during the process we just talked about, your big block of code gets placed into what we're calling for now process memory at some address. And then there's also section headers and symbol tables, but we're not going to worry too much about what those are for now. Okay. So let's talk about what an executable is in terms of like what is required. So every executable has three things that have to be there in order for the program to run. So the first is an offset in the executable file to copy code and or data from. So we talked about how we have our blob of executable data somewhere in the executable. That is going to get copied to memory. So the information on where that is and how big it is has to be in a place in the executable that's correct and easy to get to. So the operating system has to read the file and know where this is and know how to do this. Otherwise, the process of copying it into memory and then transferring execution to it won't work. We also have an address in what we're calling virtual memory. It's a topic we'll talk a little bit more about in a few slides. But we have to have an address to put it at, right? So if we look at our diagram here, it has to know where in memory we want it to be. And some stuff doesn't care. It can go wherever it wants. But historically, everything wants to go at a fixed place. And this is very slowly changing to be more fluid and randomizable. We also need another address within our block in virtual memory that we moved everything to start execution from. And it's pretty rarely the first byte of the first instruction. So even though we are copying this big blob, our start might be somewhere in the middle. And this is decided by either the programmer or the compiler or any number of other factors that go into packaging all the executable code together. But it's very rarely the first byte of the first thing we copy. It's usually somewhere in the middle. Okay. So again, I just want to reiterate that these can't be obfuscated. Like the program wouldn't work if you don't have these three things at a minimum. And so what I find a lot is a lot of the students I work with were like, well, if I'm writing malware, wouldn't I just make these like hard to figure out, or like I just change it so that they can't figure it out? Well, if you change it so that the OS can't figure it out, then it can't run. So there's some disconnect. And obviously you can obfuscate and do all sorts of other stuff. But at the end of the day, these things have to exist in the base executable. Okay. So let's talk about what is a process, right? I think, again, these are topics that you guys are very used to dealing with, but understanding them fully is very important for the exploitation process. So what is a process? So every process is effectively just a block in memory in what's called virtual memory that has an address range from 0 to some maximum. So virtual memory is this concept that it's transparent in that one process should not be able to see another process by default. And historically, this is because before we had virtual memory and other stuff, everything's shared memory. And if everything's shared memory, then one process can write over another process's memory regions and corrupt it. And that is how we got lots of crashes and problems in early computing. And then all the processes, when they want to ask to do something, like with the hardware or other processes or the operating system, they ask the operating system to do that for them. So you're allowed to kind of play in your own sandbox and kick up as much sand and mud as you want. But if you want to interact with other stuff, you have to ask the operating system via the kernel for permission. Okay. So virtual memory refers to kind of a set block of memory that every process sees. So you could think of it like a housing tract. All the houses are identical, but none of the processes in each house can see any of the other ones by default. This is kind of the idea. And historically, there's a very segmented approach to memory where you have this is at this spot, this is at that spot for all the components of a process. Those being the text segment, which is your program code that gets copied in. There's the stack and heap, which are used for control flow and memory, like variables and data management. You also have what's called the data segment and the BSS segment. These are for things that are statically defined or statically assigned by the programmer. Again, these might be concepts that are unfamiliar if you're not used to dealing in C or C++. But things like when you say X equals hello world, and that string hello world can't change, right, by the rules of most low-level languages like C, C++, that gets assigned to data because it's a predefined static piece of data. So it knows it's never going to change. It knows it's going to need to reference it. So it puts it in data. This is kind of the opposite of things like web servers. They don't know what URL you're going to request. So they use the heap to dynamically allocate memory when you make a really big, long URL request. They need to be able to handle that in real time. Therefore, they're using the heap for that, which is designed for, quote, dynamic memory usage. And then usually every virtual memory has some location to look into the kernel space, which includes shared libraries that get mapped into the process, as well as any kernel resources that get mapped into the process. And typically your process never goes here except when you're calling your shared libraries. But effectively, these don't exist for the purposes of a person writing software, but they do exist in virtual memory. And again, this is the 32-bit layout. There's really nothing different in 64-bit other than the numbers are bigger. It's more or less the same. Because the numbers are so much bigger, there's a big empty space between all the user stuff and the kernel stuff. And that's really the only kind of major difference. Okay. So we talked about kind of like how traditional memory works. So it's typically referred to as flat memory layouts, where everything shares a big pool of memory and all the processes are having fun and doing stuff together. But what if we have data as bad code? Now, I know this is fictional. I would never write bad code, but for the purposes of this talk, I thought we'd role play a bit. So what if we have data as bad code? And data's code is so bad that it overwrites a bunch of stuff somewhere it's not supposed to because we have a shared memory layout and we're allowed to do this. Well, what if process A needed that data and now it makes decisions based on corrupted data and it causes it to corrupt more and more and more, right? So this typically has a chain reaction where in a flat memory model, if one thing causes a problem, it will cascade down to other stuff. And eventually it'll get so bad that you get something like this. Now in modern systems, this is typically caused by drivers doing this because drivers all exist in kernel space, not your normal application. You'll get a crash or some kind of exception for your application, and the rest of the system will be fine. But historically, this is why if you've ever used a Windows 95 or 98 or even ME system, these crash all the time because anything can have a problem and potentially affect other stuff on the system. So what's the difference with virtual memory? So in virtual memory, the kernel is kind of shared between everything, and each of them has their own little house on the model house track. And if data's bad code crashes one thing, it's really not a big deal because all the other ones are fine. And data's bad code can get, the processes associated with it can get closed while not affecting the rest of the system. So that's kind of virtual memory in a nutshell. So let's, now that you have to think about that for quite a while, let's talk about some other stuff. Let's do another problem. So the second problem is called handy shellcode. And typically, again, what is a CTF problem? We're presented a problem, we're given some amount of files or code or something, and then we need to figure out what the answer is based on that. So if we go back here, it says this program executes any shellcode you give it. Can you spawn a shell and use that to read flag.txt? And then it gives you the path. So this link to the program is the actual executable. And in many CTFs, that's all they'll give you. But in this one, they give you source. So you actually get the full original source code of the program. So if we look at that, I'm going to go here. I have it downloaded, but you guys can open up that file, put it in whatever IDE you like, and get your coloring as you like. But for me, I'll be doing everything on my system. If you use the Pico shell, I think it will not color code it because they turn that off by default. But your mileage may vary. So when in doubt, you can always download that locally and mess with it. So what are we looking at? We have what's obviously a C source code file. We see that it has two functions. Just trying to fit it all on one screen, but I think that's good enough. So obviously in a C program, we're starting execution at main. A lot of the CTFs will have to put some kind of introductory stuff for the way they host some of these problems. So this set vbuff and get extended group ID and set GID and all this. This is done so that when you run the program, it doesn't drop your privileges because they're using, again, this whole set GUID thing so that when you run a program, it runs as a different user than your own. So we can safely ignore those first couple lines. What we care about is here. So we have a buffer, which is buff size, which I believe was 128 up here. I'm sorry, 148, right? And then it asks you, hey, enter your shellcode. Then it calls vuln passing a pointer to that buffer that we just defined. So if we look up here at vuln, vuln takes one argument, it's a pointer to a buffer, and then it pulls in data over standard in via the getS function call, and then puts that in the buffer with the putS function call. So effectively what this is doing is it's reading in some amount of data that we provide it interactively, and as opposed to a command line argument. And then it's putting it in a buffer. So puts is historically a unsafe function call, as it doesn't check that the amount of data you're putting into the destination is small enough. So in this case, we can overwrite past the end of our buffer, right? And if we do that, we cause what's called a buffer overflow. So we want to talk about all the nuts and bolts that go into why this is a problem. And I'm sure if you look up puts, PUTS, the function, you'll see, hey, never use this ever. because of this kind of specific vulnerability. So after that, we are calling buff. So in this specific example, what we're doing is directly executing whatever we put in buff. And this is typically known as, quote, shellcode. So we're providing input that it is directly executing. So we don't need to worry about finding any vulnerabilities or anything like this, but we are directly executing whatever we put in. So what is shellcode, and after that, how does it work? So we talked about how we could go from source code to assembly code to compiled or assembled binary data, right? So anything that your program does can be represented in bytes, in literal binary, right? And this represented as binary is typically called shellcode. And the reason for that is that historically, the goal is to make a shell, aka a bash shell, or on Windows, a CMD shell. Because with the shell, then as a bad guy, we can type in whatever commands we want to do whatever we want. This is always written in the assembly language of the target. So what that means is if our target is a 32-bit Intel system, we have to write 32-bit Intel assembly shellcode for that. As opposed to if it's ARM, we have to write a different set of assembly because ARM is obviously not the same as Intel. Additionally, we may need to write some operating system specific code. So depending on what you want to do, in the case of making a process, it's typically operating system specific. So the shellcode we write for Windows, even though it's 32-bit Intel, is not going to be the same as the shellcode we write for 32-bit Linux on Intel, right? So how does this work? In today's examples, these are all going to be done on the command line locally on the system, but there's no reason that this doesn't work over the network or any number of other delivery mechanisms. It's the same code, vulnerable on one end. It's just a different way of getting your exploit to it, if that makes sense. So today we're delivering everything via the command line because it's a friendly CTF setting. But for real world stuff, you may need to deliver this over TCP/IP. You may need to deliver it over a web interface. It could be a number of things. Another kind of key note here is that we inherit the permissions of the software we compromise. So when we talk about we're going to take control of a process and make it spawn a shell, what permissions does that shell have? So it's whatever permissions that software originally started with. So this is one of the many reasons why people say don't run things as a root or administrator, right? Because if it's compromised, then the shell that the attacker makes will have administrative privileges or root privileges or whatever. Jenny, it's okay, I see it here. So the question in Discord is it possible to do something to a critical section of a process? At that level for your question, it depends what you want to do. So some stuff is locked behind the kernel, and you, as a user process, you typically cannot change things about the process on the kernel. But it depends, right? So there's some things you could change within the program as it relates to itself as a process. There's some things you can't change because they're managed by the operating system or the kernel. So that's kind of a hard to answer question because it depends. And I know that's not very satisfying, but it depends. So again, to reiterate, we have spawn a shell. We're going to do that in assembly. We can do it remotely, but for today, we're going to skip that because it takes a lot more code and we're trying to keep things relatively simple. And we're going to inherit the permissions of whatever software we compromise. So again, in our example where we're having different permissions running than our user, we're going to inherit the permissions of that process. And that'll let us do things like if that user that we're running the process as also has access to the flag file that is the problem is asking us to read, then we have permissions once we exploit the process. So I guess your next question is, okay, well, what is shellcode and how do we make it, right? This is shellcode, and this is represented in hexadecimal. I could put it in binary, but I think it's equally shocking for those not used to seeing it. So both of these do the same thing. On Linux in 32-bit assembly, they run binsh or bash. Typically binsh on modern systems is a symbolic link to bin bash or some other default shell that your system has. And so I thought this was like perfectly readable. Everybody agree? Because this is the end of the talk, just so you're aware. This is it. I just show you this and then I hang up. Okay. I'm used to having a live audience. Bear with me, folks. So obviously this is not the most readable for most folks. So how do we get here? How is this generated? What does it do? And if I gave this to you and I said, hey, run this with like some sketchy shell command, you probably, I would hope, would think twice about doing it, right? So how does this work? So I'm going to show you how this works to do the assembly problem. I guess your question might be, well, how do I get that? Let's say I don't know assembly. Let's say I'm just getting started in this. How do I get that shellcode? So luckily for you, there are a lot of resources. So if you go to Google and you Google for Linux 32-bit bin sh, boop, it brings you to Shellstorm. And there are a lot of websites like this, but Shellstorm is probably the most popular. You see there's quite a few on ExploitDB. And this here, typically it's a C file to demonstrate it, to verify that it works. But this hex string here is just the second one we have listed. And you can copy that. Alternatively, where'd it go? Alternatively, I think I uploaded this full command to you on Pastebin. I think you will have to, no, it should be fine. You'll have to CD to the problem directory for handy shellcode that's specific to your Pico account because it's not going to be the same as mine. And you can paste that in, you'll see that it works. So when we were reading our code, we saw that this is done via gets or get string or get s, whatever you want to call it. Get s reads over standard in, which is normally it's like a prompt that prompts you. So if we go, let me pull my problem link here. So what I'm doing is I'm going to CD to the directory where my handy shellcode is. So I copy that from the web page. I go back to Michelle. I CD here. Take a look at what's in here. So we see that we have the source code here. We have the binary. So these are the two things given to us. And then we have flag.txt. So you're like, haha, you fools. I will just read it. If you try and just read it, you'll get permission denied. And the reason for that is that it's only readable by this handy shellcode or hacksports users or groups, right? So when we run the binary, we get set this handy shellcode one group, and via compromising it, we then have access to read the flag is kind of the idea. Okay, so if we just run vuln just kind of as is, see how it works. We'll see it says enter your shellcode, and we'll try give flag, please. And interestingly enough, it prints it back to us as we saw from the source code. It says thanks, and then it crashes. We'll talk a little bit more about what a segmentation fault is in a minute. But segmentation fault in Linux means you done crashed. And if we had more permissions, it would actually write out a memory dump. This is what core dump means. So that if we were a developer, we could review the core dump to figure out what the bug was and why it crashed, and then presumably go fix it. So what we're going to do is either from your pastebin that is here, or if you want to copy it and copy in the command manually, we are going to echo the shellcode string in. We're using echo-e so that it translates all the hex bytes into their correct binary representation, so that it's not providing a literal slash, a literal x, etc. So I will copy this real quick. I'll show you from the web version just so it's clear like what I'm doing. Go-E. Oh, what desktop was that? Number 2. Okay, so I pieced that together. And then, so some of you might be wondering, why does he do that parentheses followed by cat? And I'll show you the difference. So if we just echo it into the program, it will correctly read in our bytes, and it will actually correctly do our shell, but it won't work, right? And so if you're wondering what the -E is, -E says basically replace these /x character codes with their actual character. So if we run this, you see that it echoes the shellcode string out, which is sort of readable, but not really. We'll say, hey, no problem, but we don't get a shell. So why not? Like, I'm still me, I'm still DG teaching instead of handy shellcode, whatever. And if I run ID to see what groups I'm in, I'm not in handy shellcode. Sorry, I know that's kind of hard to read because the prompt is really long. But you'll see kind of here, I'm just me. So why is this? So there's kind of a caveat with command line specific stuff in that if you don't add this cat thing, what happens is that because we're sending data in over standard in, the process on the receiving end, in this case, our vulnerable process, will consume all of standard in, and then it'll say, hey, you have no more input for me. So I'm just going to close because I'm done doing my stuff. And so bash, when it starts up, if it doesn't have standard in, it has no way to get input from you, the user. So you can't type commands, you can't do anything. So bash kills itself. So by adding in this cat will hold open standard in for us, and we will get a shell. So you notice I didn't go back to my shell. What happened? So if I type ID here, you'll see, hey, cool. Now I'm in handy shellcode. So I am running as the handy shellcode user within the vulnerable process, and it's doing something different. So if we ls, we see, hey, we could run all of our Linux stuff. I don't know if there's like an official hacker term for this, but I call it like a janky shell. It's obviously not great. And you'll notice you can't do stuff like push up, can't push up. There's no command history or anything like that. But this is something you'll get very intimately familiar with through pen testing and exploit dev and all this stuff, is these janky shells. And we could make a nice shell, but it's kind of outside of our scope for today. But obviously, we're able to run Linux commands and bash commands. So if we do cat flag.txt, we get the answer. And again, this is done by taking over the process, spawning a shell. This shell inherits the permissions of our vulnerable process, which allows us to read the flag file out. Question is, has it been significantly less common to see exploits in code with modern tooling, /scanners, /etc.? So that's the first part of the question. I think what you're asking is, are vulnerabilities less common because of things like code auditing tools and code scanners and stuff like that? If that's the question, I would say obviously no, because we still have problems all the time. I think it's only pulled out the lowest hanging fruits from most code. So there's still a wide variety of vulnerabilities that come out every year, and many of them are your kind of basic buffer overflow just hidden behind layers of code complexity, right? So for example, that font vulnerability we showed earlier was like a pretty traditional, I want to say heap overflow, might be a buffer overflow, but pretty traditional overflow, which ends up with kernel level RCE. Second part of the question is, do you expect to see this form of exploitation become extremely rare as scanning tools get better? So I don't think so. I think kind of what we'll address at the end of this presentation is that some stuff is different, but not gone, right? So hackers adapt and figure stuff out. And as code becomes more and more complex to support like higher level languages, I guess maybe is the best description. So things like, I don't know, pick your current favorite thing that your professor is trying to tell you is the greatest thing ever, like R, I don't know, pick some language that is relatively new that nobody actually uses, but everybody thinks is awesome. I don't know if Joe's listening, but I'll say Go. People say Go. Everybody uses Go for some reason, even though nobody uses Go. Obviously, there's a lot of complexity to go from that back down to the assembly level, and that leads to vulnerabilities, and et cetera. Other question I had was, if we were not given the source code, how would we solve this? So the short answer is that we do the reverse process of compilation. We go from executable back to assembly, and assembly lets us see what the program does, and from there we can work on it. There's also a way to go from assembly back to representative source code called decompilation. So that's the act of trying to reverse the act of compiling source code into assembly. However, there's a lot of information lost in the source code to assembly translation that we can't get back. So that's why it's representative. It is functionally equivalent source code, but it's not going to look identical. So I can show you as a quick example, Ghidra and Shellcode. I think I already had this. If I can learn how to type. Give it a second. So Ghidra is broken. That's cool. New project. Cool stuff. Work with me, Ghidra. In this talk, DG learns how to use Ghidra for the first time. What do you want? Stuff. Cool. Okay, very exciting. Let me do this cool dragon logo thing. And then we're going to import our binary, right? So we're not using source code for this. It is here, handy shellcode. And it asks for the type of executable, but it figures it out magically. So we, like most things, we just keep clicking next. Do you want to analyze? Well, obviously I want to analyze. Sure, do all those things. And eventually you'll see that it's kind of filling in colors and looking real matrix over here. We're going to search for the main function. And eventually it will figure this out. Ooh. It's busy trying to load everything. All right, so we do here, and then in theory, it's the same button as IDA. Oh, there it is. So we get source code over here. I do not know how to make this bigger for you, unfortunately. But we get source code that looks really ugly, but it's more or less the same thing, right? And you'll see it's kind of filling in the blanks as it's analyzing it. So we get our strings in here. We see that it's, puts into your shellcode, vuln, and then it doesn't know the name of the variable. So it's doing all this and figuring it out. And so this is a disassembler that is hooked into a decompiler. So it kind of does all the steps for you. And the two I'd say most popular are Ghidra or Ghidra, as it's probably pronounced, as well as IDA, IDA, Interactive Disassembler. Those are probably the two most common. But there's a lot of disassemblers and a lot of decompilers out there, depending on your target language and executable format and architecture and all that. So that is the short answer of how that's done. And we're just going to leave that open. All right. So going back, we got our flag. We're going to throw that in real quick. Oops, if I could find the window. All right, so we're still in our shell. If you're stuck in your shell and need to figure out how to get out, you can type exit, which will kick you back to your kind of normal user shell. We're going to copy this, go back to our flag, submit that. Boom, we solved another one. Cool. We're up to 100 points, feeling real good about ourselves. We're a little short on time, so I'm going to go a little bit fast. We've been doing kind of Q&A in between, so I don't think we're too bad. So overflow 0. This should be easy. It's always very motivational, right? overflow the correct buffer in this program and get a flag. It's also found in blah, blah, blah. So again, we have our source. So let's go ahead and take a look at our source code. Let me kill this real quick. Okay, so we have overflow 0. Let's look at that. So what do we have? So again, it's a C file. Again, we have what looks like a fairly similar setup. We have a vulnerable function, we have a main. At the start of main, it's opening a flag file. So remember, this happens on the challenge server, not locally. But we're opening up a flag file, we're making sure that worked. And then we are copying the contents of the flag file into this flag buffer, which is defined globally up here in char flag, right? And then we are setting up a signal handler. So signaling is a Linux process control thing. So you can control what happens under certain conditions, like if the process crashes, if it is stalled, any number of other conditions. In this case, we're doing sig-seg-v, which is a segmentation fault handler. And I guess the short description of that is if it crashes, it will call this function. If we look at the function up here, it's this sig-seg-v handler up here. We see that it will print out the flag for us if we cause this to happen. So that's pretty interesting, right? And then it will exit. So it will gracefully exit after catching this segmentation fault, and in doing so, print out the flag. So if we scroll down a bit, let's think, whoa, okay. So it obviously wants us to crash it because that's how we get the flag. How do we do that? Again, they do the setup stuff so that we don't drop privileges, just like the last one. And then down here is the remainder of main. It checks if there is a command line argument. So argc is the number of command line arguments. So as long as it's greater than 1, it's happy. And then it takes the first argument and passes it to the vuln function. And if we look up here, the vuln function is taking, again, a character pointer input. And then instead of doing the get s, put s kind of stuff, it's doing str copy from our input to the buffer. And the buffer is only 128 bytes long. So the thought here is, again, very similar to puts. String copy is a function that is vulnerable if you don't do any bounds checking on it. And if we provide more input than the buffer can handle, then we will cause some problems. And we'll talk about kind of why and how. But at a base level, all we know is, like, if we give this too much data, it will overflow the buffer and that will corrupt memory. And from there, we'll get a crash is kind of the long and short of it. So before we get into some of that, let's talk quickly about kind of how assembly works. So assembly, in all variants of assembly, whether it's Intel assembly, ARM assembly, whatever, is a mnemonic language. So what that means is that for every plain text instruction, there's a direct translation to the binary representation and vice versa. So if you have the binary, you can go back to the plain text representation. And so this is how disassemblers work, is that they read the bytes of the executable, and then they determine what the instructions would be and work from there. So on the bottom are some examples of Intel instructions. And their corresponding binary translations. And I think some of you have met me and seen me read some of the Intel, because I'm frankly pretty used to 32 and 64-bit Intel, that I can read a lot of the assembly and like know what the code is. This is not normal. I am weird. It is okay if you can't do this. But over time, you'll start picking up, like, the CD80 is a very notorious instruction that's very common for 32-bit Intel. So how does this process work? Well, when the assembly language and the processor is designed, they have a giant mapping of basically every single bit of the instruction means something in the binary format, and that maps to a human readable version. So if we have this instruction down here, which is add EAX and then some 32-bit number, this is its binary mapping. The first 6 bits indicate that it's an add instruction, and then from there it's broken down into little pieces to say, I want to add a 32-bit number to a register, and this is the register I want to pick based on these bits, and blah, 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 right? It's obviously very complicated at a low level, but you don't need to know this. This is just so you understand kind of how this works and how a disassembler does what it does. So I translated our shellcode, and again, like this is super readable and really easy for you, and you probably don't have any questions, and everything's cool, right? But effectively, we're going to teach you how processors and assembly language works at a high level in what I hope to be 60 seconds. So all assembly languages have the same 3 basic concepts. They have instructions, they have registers, and they have memory. And this, again, applies to every single processor, every single assembly language. It's just the specific verbs and syntax change. So at the assembly level, again, we are 3 things. On the left in yellow, we are instructions stored somewhere in memory. And those instructions are executed by the processor to change things in registers. We'll talk about what those are in a second. Those are in the middle in green. Or change things in other parts of memory, shown on the right in blue. So we're going to talk about each of these 3 so that you understand it. So instructions in assembly execute sequentially most of the time. So there are instructions that change what the next thing to execute is and jump around. But at a base level, you're going instruction 1, instruction 2, 3, 4, etc., unless kind of otherwise specified by the instructions themselves. Instructions are a name or a keyword followed by 0 or more arguments. Another name for these you might hear is opcodes, because in original assembly language documentation, they were like operating or operations codes. So you would write your add would be the opcode to add things together. And I'd say most modern assembly languages are fairly readable, but some of the older ones were a little more hard to read. Therefore, opcode kind of made more sense there in that you had to learn what they did. Instructions kind of break down, and they really only do 3 things. So a lot of folks I meet think assembly is complicated, but in reality, it really only does 3 things. You either are doing arithmetic, so this is computations or calculations of some form. You are doing data retrieval or data storage, so we're either storing the results of our computations or getting new data for the next computations. And that storage is either in memory or on registers, which we'll talk about next. And then finally, the last thing is control flow, so deciding what to execute next. So based on your calculations from the data you retrieved, you can decide where to go next and execute different branches of code. So if you think like an if statement in a normal programming language is just an assembly version of retrieve data, perform a calculation on them, and then decide where to go next. And then from there, you have another subblock of code, whether you passed the if statement or you didn't pass the if statement, goes to different places. But logically, these are very simple languages. It's just that they're individual things they do are so small that the code is very long and therefore looks complex. What's kind of interesting about at least Intel processors is that code and data coexists in memory. And this is what's called a von Neumann architecture, in that there's no distinction between code and data in a kind of high level sense. The alternative to this is what's called the Harvard architecture, where code is supposed to go in the code places and data is supposed to go in the data places, and never the two should mix. So this is things like ARM is an example of a Harvard architecture, I believe. AVR, pretty much most of the microcontrollers used to nowadays are using a Harvard architecture. But Intel, von Neumann, and everything's shared. And that leads to a lot of our kind of vulnerabilities at the back end here. So we talked about instructions. Let's talk about registers. Registers are buckets of data on the CPU. So you could think of them like a fixed size variable in other programming languages. And the size that this variable is limited by the processor itself. So when we are saying 32-bit processor, 64-bit processor, this typically refers to how big its registers are, and at some level, how big the data it can work with easily in like one operation is. So obviously you can do bigger computations and all that kind of stuff, but at a base level, the processor bit size is the same as the register bit size. Some registers are general purpose in that you could do calculations and do whatever you want with them. Some have very specific uses and are non-writable or non-readable or any number of other things. On 32-bit Intel, the register names are things like EAX, EBX, ECX, etc. 64-bit is basically the same, but it adds a RAX, which extends the register out to 64-bit. And there's a bunch of subdivisions of this, which you can look up in your free time, but that's kind of the breakdown. And lastly is memory. So memory is kind of a very simple concept that I see a lot of folks have a hard time describing simply, but memory is just a list of values, and you identify which value you want based on an address. So the simplest way I've thought to think about this is that imagine you have a one column Excel, right? And you just say, I want data number 1, data number 2, data number 3 to pull out the values you want from this long list of values, right? It's basically how memory works. And the CPU via instructions reads to or writes from things in memory to move stuff around, change values, load values, etc. And as a kind of side note that is, I guess, a little foreign to folks, is that most of the memory access in modern computing is done on boundaries for performance reasons. So the CPU is much happier working with 8-bit or 16-bit or 32-bit addresses, alignments, as opposed to going like 1 byte at a time, if that makes sense. And this is because how it's hard-coded into the processor, and it's kind of a common theme for pretty much any processor you work with. Okay. So all of this was kind of to explain like how assembly works and how shellcode works. So even though that shellcode we looked at is very unreadable, the short version is that it calls a system call, which runs a process, and you give it a string, which defines the process you want to run. So the equivalent is OS system, BNSH of Python. But in Linux, this is like what's called a system call, and most of the libraries offer this. But this is the kind of internal version of this. System calls in C, again, are via functions. In assembly, the way it works is that you load up the registers with certain values, and then you tell the kernel, hey, I need help. And it reads the registers in the CPU to figure out what you wanted and then tries to act on it. In our case, run a process to spawn a shell. I think we're getting relatively close to the end here, if not at it. So I wanted to pause and verify that, and then maybe take a question or two. And I'm happy to keep talking to you guys on Discord. I just have to put the next person on.
Yeah, it looks like you've got about 5 minutes. So any questions from now till 4:25 is good to go.
Okay. If you guys have questions, just shoot them at me. We didn't quite get to finish. We only had like 20 more slides. That's cool though. But I'm sure the folks at Swift will make this available to you, and you're welcome to ask me any questions on Discord if you have some trouble with the remainder of the material.
Sure thing. Yeah, so if anyone has any questions, feel free to type it in the chat. If you'd like to ask on voice, feel free to kind of raise your hand on Zoom, and I'll allow you to unmute yourself. So we'll just give it a quick second, see if people are still typing it in.
Everybody went to bed, sorry.
All right, well, it doesn't look like there's any other questions. Just wanted to say thank you so much, Data, for really deep dive into the technical information, just revolving around binary exploitation. Oh, looks like Hannah's raising her hand. Hannah, I think you can unmute now.
So my question was like, if we want to practice just like reverse engineering, what resources would you recommend?
Sure. You reminded me. I kind of knew exactly what you're going to ask, right? Is the first question. But so what I would recommend is kind of go through Pico CTF. You kind of have a start on some of these, and they're building on a theme for the binary exploitation ones at least. There's a lot of additional reading you could do that's here. And again, you can look at the slides afterwards if you need it. I think the best way, if you're interested in learning from a CTF perspective, I think the best way to do that is go on CTF Time. It is a constantly updated calendar of events. So you can find new challenges coming up, look at old challenges. There's also write-ups for all the stuff. So all the problems we worked through today, somebody on the internet has posted a walkthrough for to explain how it works or how the solution works. There's also what's called, what we're doing today is called a Jeopardy CTF. There's also attack defense CTFs, which are more like CCDC, where you have something to protect or something to go after. So I think just doing it is really, there's really no substitute for. There's obviously a lot of books on reverse engineering and exploitation that you could read, but they're no substitute for just doing it and seeing, what you need to get better at.